like it used to be, we found a couple, and now we've found literally thousands. Because they put up a satellite whose purpose is to look for them, and it did a very good job. So the chapter 17 homework is due today. The chapter 17 quiz will be in SI today. Chapter 18 quiz homework is due on the 28th. That's not next week, but the week after on Monday. And the quiz will also be on the 28th, that Monday, and that will be in lecture. And lastly, the exam on chapters 16, 17, and 18 will be on the 30th. That is the last scheduled day of class. That's the Thursday of the last week. And the labs on the 21st and the 28th are for makeups. We've done the last lab now. So we had started talking about how we figure out where things are. So let's talk about celestial distance. So the distances to most celestial objects, yes, we can report them in like meters or kilometers, but it gets kind of silly. The numbers get so big, they're hard to understand. So we tend to use units based on things we can deal with. So in the solar system, distances are primarily measured in astronomical units for a couple reasons. One, it's a convenient reference. It's the distance from the Earth to the sun. And two, for a long time, we knew everything's distance relative to each other, but we didn't actually know the absolute distance. We knew how many astronomical units away from things were because you could work things out through geometry, but we didn't know how big an astronomical unit was. But once you get that, the astronomical units, that's the distance between the Earth and the sun. The next distance we tend to use is light years. This is the distance that light travels in a vacuum in 1 year. The primary, this has the added bonus of telling how long into the past we're looking. So if something is 4 light years away, the light coming to us from it left it 4 years ago. If something is 13 billion light years away, the light coming to us left it 13 billion years ago. So one of the interesting things about astronomy is that we can look into the past by just looking into the distance. The further away an object is, the further away in the past it is. Oh, oops. And lastly, there is the parsec. The parsec is a convenient unit of distance that's based on one of the ways that you can actually measure the distance to a star. So one of the ways you can measure the distance to a star is via parallax. And if a star has a parallax of 1 second of arc, which is 1/60th of a 60th of a degree, it is 1 parsec away. If it is less than 1 second of arc, it is more than 1 parsec away. So a parsec is just a thing with geometry. It's this effect of parallax. If you're looking at something that's near you, if you look, for example, if you look at it with one eye and then switch to the other eye, you'll see it appears to move across the background of what you're looking at. The same thing happens when Earth goes from one side of its orbit to the other. The nearer stars appear to move across the background of farer stars. This apparent annual motion of a star is called parallax. The fact that parallax was not observed was one of the arguments against heliocentrism. The issue was actually that parallax is so small it couldn't be observed. People didn't realize quite how far away stars were. And the closer the star, the bigger the shift from parallax. The thing is, the nearest star is more than a parsec away. So the largest parallax observed for a star is less than 1 arc second. So less than 1 3600th of a degree is small. So the formula is actually quite simple. To find the distance in parsecs, you just divide the parallax, you do 1 over the parallax in arc seconds. So Proxima Centauri is the nearest star to Earth. The annual parallax of that star is 0.762 arc seconds. The distance to that star is therefore 1 over 0.0762 or 1.31 parsecs, which is a little over 4 light years.
That's the closest star to Earth.
That is the closest star to Earth. So 1 parsec is 3.26 light years. It's also why scientists why there was this huge plot hole in Star Wars where Han Solo talks about doing the Kessel Run in less than 12 parsecs.
Makes a whole lot more sense now that I'm hearing you talk about here.
There were a bunch of hoops jumped through in later movies to make that not sound stupid. So they did in fact fix that in the movie Solo by making the trick being that we literally took a shorter path. Now here is an example with Sirius. The brightest star in the night sky. The annual parallax of this is 0.376 arc seconds. So its distance will be 1 over 0.376 or 2.66 parsecs, which is between 8 and 9 light years. Sirius is quite close and also big, which is why it's the brightest star in the sky. So parallax cannot be detected with the unaided eye. You need a pretty decent telescope. And in fact, it was not detected until 1838. That was when the first parallax was detected. And even for the very closest stars, parallax is very small. The parallax for the closest stars is like the width of a dime at a distance of 6 kilometers. This is how small the change we're talking about. And you can only really use parallax within about 100 parsecs, so about 300 light years. There's actually kind of a ladder of ways we measure distance that work further and further out that you can chain into each other. So let's talk about stars. We'll start by talking about the star that is easiest to observe. That is the sun. So the closest star to us is 1 astronomical unit away. It's the sun. So a star is a big ball of hot gas. Well, plasma, but yeah.
Isn't the sun technically, like, if you look at most, if not all, the stars in the whole galaxy that's been discovered, the sun is technically the smallest, isn't it?
Oh no, it's nowhere near the smallest. It's sort of middling.
Oh, in terms of overall size?
Yeah. There's a lot of smaller stars than the sun. They're in fact,
I mean, as far as the ones we can see, like in the night sky, those are.
Oh, the ones we see in the night sky tend to be quite big, because the smaller stars are smaller and thus dimmer and thus harder to see.
Right.
There's lots of them. They're just harder to see. So the ones we see in the night sky tend to be much bigger than the sun.
I think most of them are bigger.
Like lots bigger than the sun. But if you actually like look at the stars, the sun is middling to low in size. There's a lot of smaller stars. Turns out the way it works with distribution, you get fewer big stars and more little stars. Has to do with how stars form. But stars are just balls of hydrogen and helium compressed under their own gravity until they get hot enough that fusion starts. I mean, they're at some fundamental level quite simple. It's just a ball of very hot, well, gas. Well, it's hot enough to be a plasma, but yeah. It's a self-luminous sphere of hot gases that's energized by a nuclear reaction and held together by the force of gravity. And the thing that makes it a star is that fusion started. So the sun's the nearest star to Earth, and it's enormous in size relative to the size of Earth. It's about 100 times the diameter of Earth. And when you think about volume, that makes it so much bigger. But like, if you took it, you can put 100 Earths across the sun. A little bit more, actually. So here's a short video about the sun.
While billions of stars are scattered throughout the universe, the one at the center of our solar system plays a special role for us here on Earth. Our sun formed about 4.5 billion years ago in the Milky Way galaxy's Orion Spur. It was born when a cloud of dust and gas, known as a solar nebula, collapsed. And in the middle of this formation, matter condensed into a burning ball of gas that became our sun. The sun's fiery nature, along with a tremendous gravitational pull and an extensive magnetic field, helped it to become the heart of our solar system. The sun can be divided into 6 layers or regions: the corona, the chromosphere, the photosphere, the convective and radiative zones, and the core. In terms of atom count, the sun is about 91% hydrogen, the sun's fuel, 8.9% helium, and 0.1% heavier elements, such as carbon and nitrogen. Due to the sun's extreme temperatures, these elements stay in a gas-like phase called plasma. In the core, temperatures reaching at least 27 million degrees Fahrenheit, combined with the sun's powerful gravity, fuse together hydrogen molecules to create helium. Called thermonuclear fusion, this releases an enormous amount of energy in the form of radiation, electricity, solar wind, and, as we experience on Earth, life-giving heat and light. Such volatility is contained thanks to the sun's tremendous gravity. It's strong enough to hold the solar system intact and is primarily due to the sun's size and mass. Our sun is the largest and most massive object in the solar system. It's more than 100 Earths wide and could theoretically fit all 8 planets inside nearly 600 times. It also contains approximately 99.8% of all the mass in the solar system. Because of this mass, the sun has a great pull on the fabric of space, creating a gravitational force that causes nearby planetary bodies to be drawn toward it. This gravitational pull allows the sun to hold together a system of 8 planets, potentially dozens of dwarf planets, at least 170 moons, and countless comets and asteroids. Without the sun's gravity, these celestial bodies would drift off into deep space. Another critical property of the sun is its magnetic field, which encapsulates the entire solar system. Called the heliosphere, this force field protects the planets from harmful cosmic radiation. It's caused by the sun's plasma pushing electrically charged particles toward the star's poles. This process turns the sun into a giant magnet. Although the sun's magnetic field is invisible to the naked eye, its effects on the sun's surface are dark areas called sunspots, which mark strong pockets of magnetism. On Earth and on some of the other planets, the sun's magnetic field interacts with their atmospheres, resulting in beautiful auroras. Despite its size and strength, the sun will not last forever. In about 6.5 billion years, it will run out of its hydrogen fuel, expand to envelop Mercury, Venus, and even Earth, and then collapse into a small star known as a white dwarf. In the meantime, the sun will continue to play a critical role in the system that bears its name. The sun's protective magnetic field, tremendous gravitational pull, and ability to create vast amounts of energy will protect, contain, and give life to our solar system.
So, some basic information about the sun. Its diameter is 1.4 times 10 to the 6 kilometers, or 8.6 times 10. So 1.4 million kilometers, or 8.6 times 10 to the 5th miles. Its mass is 2 times 10 to the 30 kilograms. That's enormous. Again, 99.8% of the mass of the solar system is in the sun. Most of that remaining 0.2% is Jupiter. It sun's really big. The density is about 1.4 grams per cubic centimeter. It's a ball of gas. It gets dense in the center. It's very dense in the center, but it's not so dense at the edges. The period of rotation at the equator is 25 Earth days. It's slower at higher latitudes because, again, it's a big ball of fluid. It's not all flowing at the same rate. And the fact that it's not all rotating at the same rate has effects on it where it kind of ties the magnetic field up in knots and helps create solar weather. And the distance from the Earth is 1.5 times 10 to the 8 kilometers. 150 million kilometers, or 9.3 times 10 to the 7, or 93 million miles. And the sun has several layers. There's the inside portion of the sun, which you can divide into the core, the radiative zone, and the convective zone. We're not going to talk about those much in this class, but basically the core, which is about the innermost 25%, is where the actual fusion occurs. In the radiative zone, energy is transmitted via radiation, light, and then in the convection zone, it's transmitted via convection, currents, flowing currents of hot gas. The surface that we see is called the photosphere. That is the point where the sun becomes transparent. Above the photosphere, the sun is transparent. We can see through it. Below it, it's opaque. That's why we see the photosphere. It's called the photosphere because it is the sphere of light. It's the thing that emits the light that we see. Above that is the chromosphere, which is a layer of very hot gases that are, the hydrogen gets excited and they glow red. Hence the sphere of color, chromosphere. And above that is the sun's outer solar atmosphere, which is quite thin, and that is the corona. And the corona is sort of spiky. And because it's spiky, they called it corona, like for crown. Spiky things get called crowns. Same reason that the coronavirus is called a crown, is because it is spiky. So the photosphere is the bright visible surface of the sun. Its temperature is around 6,000 Kelvin. It's by mass, 75% hydrogen, 25% helium, and about 1% carbon, oxygen, nitrogen, neon, and others. I know those don't perfectly add up, but just general rule of thumb, stuff in the universe tends to be about 75% hydrogen, 25% helium. We'll get into why later, but it has to do with what was actually created at the very beginning of the universe. And when viewed up close, the photosphere's surface appears to have a granular texture. It's got little granular structures on it. Each granule is a hot spot caused by an individual convection cell bringing thermal energy up to the surface, and each granule is about the width of Texas. Sun is huge. On the sun, there are also sunspots. These are huge patches of cooler and therefore darker material on the surface of the sun. They are temporary. They last for a little while and they go away. They're distinctive features of the photosphere. And we've been observing them since about the 1600s, since Galileo. And in the late 1600s, this was an unusually cold period on Earth, marked by also an anomalously fewer number of sunspots. So in Europe, this was known as the Little Ice Age. So there may be a strong correlation between solar activity displayed as sunspots and global climates on Earth. The main problem is our sunspot data only starts in the 1600s. And we can't go back any further. We have good climate data past that, but the sunspot data is only starting then. So we don't know what's going on in the sun in the past. So we really have one data point, which is a very hard thing to determine if that's a coincidence or not.
I wonder, I don't want to assume that global warming has an impact on the sunspots.
Oh, global warming will not affect the sunspots. The sunspot, if the solar activity might affect, so the theory here is that there may have been a difference in solar activity, so the Earth might have been heated less. But we don't know because one data point. So it might have also just been a coincidence. Global warming, so you could have an effect on top of global warming, but they're separate effects.
I just wonder if maybe the number, or at least maybe the frequency of sunspots is changing.
Oh, it does change. I think it's been relatively steady recently, as in, like there was another dip at one point, but there wasn't a huge change in climate. So here's a close-up of the sunspot. These smaller dots are the granules. The sunspot is the big dark area. So sunspots actually correspond to magnetic activity on the sun. So there's actually like a pattern. So the abundance of sunspots varies according to an 11-year cycle also. There's no apparent climate change at that scale, but the Maunder minimum was a period of time where there were much fewer sunspots each cycle. So the abundance of sunspots varies through an 11-year sunspot cycle, where the abundance climbs up and then sinks down again. Each sunspot cycle begins with the appearance of a few sunspots near around 30 degrees north and south latitudes, and the number of sunspots slowly increase with a maximum number in the middle of the cycle around the 15-degree region, and then the number of sunspots slowly tapers off in the last half of the 11-year cycle. And they actually move where they show up on the sun as well through the cycle. They also have a magnetic polarity, because it turns out sunspots are tied to where magnetic fields are punching through the surface of the sun. And each 11-year cycle is similar, except the polarity reverses each one. So the 11-year sunspot cycle is actually a manifestation of a more fundamental 22-year magnetic cycle. And through that 11-year cycle, they start further near to the poles and then move towards the equator through the cycle. And there's these, you could look at these charts of where sunspots are located through the whole cycle. It's called the butterfly chart. Because it looks kind of like butterflies. There are also more dramatic structures than sunspots that occur. There are flares and prominences. Flares are bright explosive events that occur on the sun's surface. And prominences are enormous filaments of solar gas that arch out and over the sun's surface. They're super dramatic. They can extend hundreds of thousands of kilometers outwards. And because they occur along the outer edge of the sun, they're particularly evident during solar eclipses. So here's a major solar prominence over here, this huge arc of gas coming out. And also the bright yellow areas are flares. The outermost atmosphere of the sun is the corona. It's the pearly white halo or crown extending far beyond the solar disk. It can be seen during total eclipses of the sun, or if you're using a sun that you could block the sun out and image the corona. You can block out the photosphere with, but it's visible during total eclipses of the sun. The corona can be interpreted through the sun's outer atmosphere. And it gets heated by the sun's magnetic field to being quite hot. It's about 1,000,000 Kelvin, but it's very thin, so it doesn't really do much. And prominences occur within the corona region of the sun. And at the extreme high temperatures that the corona produces, protons, electrons, and ions can get enough energy to escape the sun's atmosphere. They're actually only being held in place by the sun's magnetic field. And so there are what are known as coronal holes, which are sort of gaps that solar material can escape through. So these particles get accelerated enough to escape the sun's tremendous gravitational field. And this creates what's known as the solar wind, which is a constant outflux of material striking planets. So changes in the solar wind and solar activity might affect climate on Earth. We don't really know yet. And the solar wind extends outward from the sun for at least 50 AU. I think it's closer to 100. And the heliosphere is the volume or bubble of space that's formed by the solar wind. And I think it's somewhere between 50 and 100 AU out from the sun. And virtually all the material in the heliosphere emanates from the sun, because the Voyager probes passed outside the heliosphere and they were able to detect that transition. But I don't remember how far they were from the sun when that happened. So generally the heliosphere, the edge of the heliosphere is used as the transition to interstellar space, the space in between stars. The heliosphere is the area dominated by our sun. Once you go beyond it, you're in interstellar space. So, and the solar wind constantly comes outward. And if your planet doesn't have a magnetic field, it can strip away your atmosphere, things like that. Part of why Mars's atmosphere is so thick. It lost its magnetic field and the solar wind started dripping away, and why Mercury doesn't really have an atmosphere at all. So in the extreme high temperatures of the corona, protons, electrons, and ions are furnished with enough energy to escape. I already did this, sorry. So inside the sun, it is so hot, atoms are not able to exist. The electrons get torn free from the atoms, and you just have nuclei and electrons flying around in a gas of charged particles, which is a plasma. So this is what's known as the state of matter known as a plasma, sometimes referred to as the fourth phase of matter. This is basically, it's where a mixture of ions and electrons exist as a high temperature gas. And in the sun, it's basically nuclei and electrons, because it's mostly hydrogen. So it's just free nuclei flying around and free electrons flying. And the temperature at the central core of the sun is about 15 million Kelvin, and the density is 150 grams per cubic centimeter. And the innermost 25% of the sun, the core, is where actual fusion occurs, where hydrogen is consumed to form helium. I don't know why I said that backwards. But so just the innermost 25% is where actual fusion occurs. And as you move outward from the core of the sun, both the temperature and the density decrease. It gets less dense and less hot because everything in the center is hot and squished by everything above it. And it's the nuclear fusion of hydrogen into helium that's the source of all the sun's energy, and also the thing that keeps the sun from collapsing even more. So the sun is sort of a balance between the heat from nuclear fusion pushing outwards and gravity pulling inwards. And in the sun and other similar stars, nuclear fusion takes place as a three-step process called the proton-proton chain. What occurs? Two protons will merge to form deuterium. These deuteriums will merge with another proton to form helium-3, where one of the protons turns into a neutron. And then two helium-3s will merge to form helium-4 and two free protons. No one who is doing fusion on Earth is planning to do the proton-proton chain. It just takes too much energy. Like you have to get too hot and too dense to pull it off on Earth. So on Earth, we can't get the densities of the sun, so we have to get even hotter to do any sort of fusion, and we do easier parts of it. We generally do deuterium. So here's how fusion powers the sun.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse, and that's very, very rare.
To force protons together takes immense amounts of heat and pressure, generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
But with gravity crushing things down, things get close enough together, and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
Yeah. So it's taking hydrogen, and by combining hydrogens through this three-step process, the two hydrogens form a deuterium plus a positron and a neutrino. Then the deuterium merges with another hydrogen to form helium-3 and a gamma ray, and then two helium-3s merge to form helium-4 and two hydrogens. So it's taking the raw material of hydrogen and combining four hydrogens together to create helium. And also some energy These all have some energy. And the mass of helium-4 is less than the mass of 4 hydrogens. It's converting mass into energy. So what you get is, 4 hydrogens is 2 helium-4s plus 2 positrons, a neutrino, a couple gamma rays, and some energy. And the amount of energy released by the conversion of mass matches up with Einstein's equation for E equals mc squared. So if you look at the mass of all of these, I mean, this is massless, it's just light. But the mass of these things, it's less than the mass of the 4 hydrogens by a little bit. And that difference is what's converted into energy and is emitted as energy. But the sun will eventually run out of fuel. It'll run out of hydrogen that it can convert into helium, and it will die. So it won't use up all the hydrogen in it. It will run out of hydrogen in the core that it can actually use. And then a process will occur. We'll talk about it a little bit. So yeah, about 6 times 10 to the 11 kilograms of hydrogen gets converted into 5.96 times 10 to the 11 kilograms of helium every second. And you can see it's a, like a little less than 1% lower mass. And with a total mass of 10 to the 30 kilograms of hydrogen, scientists expect the sun to continue to radiate energy from helium fusion for about 5 billion years. So to our understanding, the sun will run out of fuel it can use in about 5 billion years. Has a total lifespan of around 10 billion years. Been around for about 5, it'll last another 5. So it's about halfway through its lifespan. So the Earth receives only a very small portion of the sun's radiated energy. It radiates energy in all directions. The Earth only, a tiny bit of that only hits the Earth. And every second the Earth receives approximately 1.4 times 10 to the 3rd watts per square meter. That is a value known as the solar constant. Even a small variation in the solar constant would have a disastrous effects on our planet. Biota, like all the living things on our planet. Plus or minus 5%, 0.5%, sorry, would have disastrous effects. So while the sun will remain for another 5 billion years, it's expected to get a bit hotter in that process. So current life on Earth is sort of hosed in about 1 billion. Or at least we think, but we don't really know. Life may be able to evolve to deal with it, but it would have big changes, cause big changes. A sudden increase in the temperature of the sun would be bad, or a sudden decrease. So, stars are, let's talk about stars. Stars are primarily composed of hydrogen with some helium and much smaller amounts of other elements. They exist as huge plasma spheres where nuclear fusion of hydrogen to helium produces enormous amounts of energy that get emitted. And the masses of stars can vary between about 0.08 and 100 solar masses. That's the range for stars that we see. 0.08 solar masses is the lower limit for stars. If a star is smaller than 0.08 solar masses, it never gets hot enough for fusion to start, and so it is not a star. It's what's technically called a brown dwarf. The upper limit for stars is around 120 solar masses with modern mixtures of gases. Theoretically, if you had a star with just hydrogen and helium, so maybe some of the very first stars that ever existed, the upper limit is around 300 solar masses. So if you have a star that's over about 120 solar masses and try to add more mass to it, it gets so hot that it blows off its outer layers and wouldn't keep that extra mass. 1 solar mass is the mass of our sun. So the theoretical upper limits for a star with with metals, to use the astronomy term, is around, with modern impurities, it's around 120 solar masses. And then the theoretical limit, just in general, is 300 solar masses. But that requires like starting material that doesn't have any heavy elements, just hydrogen. Now, most stars actually are parts of multiple star systems, unlike our sun that's a single star. The majority of stars are, you got, like the nearest star to us, Proxima Centauri, is part of a 3-star system. There's 3 stars there: Alpha Centauri, Proxima Centauri, and I think maybe Beta Centauri. I can't remember what the third one is called. Our sun is a single star. That's a little abnormal, but lots of stars are binary stars. They consist of 2 stars that are orbiting each other. The 2 stars that are close to each other and orbiting each other. And most stars are part of a binary system. And there are also star systems with 3 or more closely spaced stars, but these are a lot less frequent because they're not as stable as a binary. But again, like Alpha Centauri, Proxima Centauri, and the other one is part of a 3-star system. Totally possible. And one of the nice things about the fact that most stars are in a binary system is we can use their orbits to figure out their masses. So here's a short video about stars.
Like fireflies on a still summer night, they gently dot and illuminate the infinite velveteen sky. Stars, be they millions or billions of years old, are all born in nebulae, clouds of dust and mostly hydrogen gas. Within these stellar nurseries, stars begin life as protostars,
Just a second.
or hot cores formed by the collection and collapse of dust and gas. As the protostars become hotter, hydrogen nuclei inside of the cores begin to fuse and create helium. It is this chemical reaction, thermonuclear fusion, that generates a star's heat and energy and causes it to shine. Stars are categorized by a number of characteristics. One of these classifications is by surface temperature. Called spectral classes, these 7 major groups range from the coolest stars, which are designated as M, and up to the hottest stars, which are designated as O. Stars are also classified by the amount of light they emit, or luminosity. Called luminosity classes, these 9 major groups range from the small, less bright white dwarfs to the large and extremely bright hypergiants. But no matter their luminosity or surface temperature, all stars eventually burn through their hydrogen fuel and die out. Less massive stars, such as our sun, release their stellar material into space, leaving behind a white dwarf surrounded by a planetary nebula. More massive stars instead blast matter into space in a bright supernova, leaving behind an extremely dense body called a neutron star. But the most massive stars, stars that are at least 3 times our sun's mass, collapse into themselves and create a bottomless well of gravity, a black hole. But from the remnants of stars, heavier elements are cast into the universe, and it is this stardust that formed the seedlings of life itself.
That statement about the size of the stars that form black holes was a little deceptive. The core of the star has to be stars usually about more than 10. I don't remember the exact one. because it's a little, I think it might be, I think it might be more like, I don't remember the line for neutron to black hole. But the core needs to be more than 3 solar masses, but remember the core is just the center of that star. The outer layers get blown off. So constellations are prominent groups of stars that appear as distinct patterns to an observer on Earth. Most of the constellation names that we use can be traced back to either early Babylonian or Greek civilizations. They tend to be named for deities. Lots of other cultures have other names for these and different arrangements of stars. For modern purposes, there are 88 official constellations that are just used to designate portions of the sky. Other than their particular patterns, they have no physical significance. Often constellations are made of stars that are nowhere near each other. Because we're just seeing how they look on the sky. They could be a lot further apart in how far away they are from us. I mean, not always, but yeah. But talking about, it's just more convenient to say, I'm talking about the thing that's located in Sagittarius than I'm talking about the thing that's located at these specific, right ascent and declination. Yeah, it's just a tool used for location at this point. So despite their non-science significance, modern astronomers use the constellations to portion the celestial sphere. Also because they've been used historically for a long time, so if you're going to compare to historical stuff. So in a similar fashion to individual stars, the constellations also appear to move westward across the sky each night. This is due to Earth's rotation. And they also exhibit an annual cycle of motion due to the tilt of the Earth and its annual orbit around the sun. But yeah, it's just a way to partition the sky. So for example, and then there's naming schemes for stars based on what constellation they're in and their brightness. So, for example, Sagittarius A star, it's A with an asterisk, is the black hole at the center of our galaxy. It's a star because it's a radio source, but it's the brightest one, which is why it's A. And then asterisms are familiar groups of stars that only comprise part of a constellation or perhaps parts of 2 constellations. So some examples are the Big Dipper, the Little Dipper, and the Summer Triangle. The Big Dipper is in Ursa Major. The Little Dipper is in Ursa Minor. And I don't remember what the Summer Triangle is. But yeah, again, the constellations are basically arbitrary. So yeah, the Big Dipper is in Ursa Major. You can see there's a bunch of other stars in it. The Little Dipper is in Ursa Minor. There are other stars in it. And Polaris, the North Star, is located at the end of the handle on the Little Dipper here. And you can find it by sort of following the 2 sides of the cup up north. So the Big Dipper can let you help find the Little Dipper, and that can also help you find where north is. Because Polaris is over the North Pole. So, the first large-scale catalog of stars that we know of was made by the Greek astronomer and mathematician Hipparchus. And what he did is he measured the location and assigned an apparent brightness magnitude to more than 800 stars. He was also the person who figured out that the Earth was precessing as it rotated. Because he was studying like ancient records of stars. Ancient for him, and this was like 100 BC. He was studying several century-old stuff from Babylon. But he compiled the first large-scale star catalog. He measured the location and assigned an apparent brightness magnitude to more than 800 stars. He assigned these magnitudes based on saying, first magnitude was the brightest star, the second magnitude is the next group that's less bright, and so on. And then the dimmest stars that he could see were 6th magnitude. We still use this system, which is kind of awful. So it turns out you could turn his system. So the apparent magnitude is the brightness of any celestial object as observed from Earth. First magnitude stars were the brightest. 6 magnitude stars were barely visible to the unaided eye. It turns out it's possible to turn actual brightness measure. You can turn this into an actual quantitative scale. And more or less keep Hipparchus's numbers. The apparent magnitude scale used today is a modified version of Hipparchus's scale, where instruments are used to actually measure how much light is coming from the star, and then you can quantify the apparent magnitude. And because it's based off Hipparchus's scale, the modern scale is such that a difference of 5 magnitudes represents a difference of 100 in apparent brightness. So the actual light is reduced by a factor of 100 when you increase by 5 magnitudes. The logarithmic scale, where the step size is that for every time you go up by 5 on it, the actual brightness goes down by 100. It's also reversed. The smaller the magnitude, the brighter the object. So the sun's magnitude is like negative 20 something. So 6 of the 7 stars at the Big Dipper have apparent magnitudes of around 2. The 7th at the junction of the handle and ball here has a magnitude of around 3. So the brightest stars in the sky are around 1-ish. I mean, the brightest star in the sky is, I think, around 0. Sirius. Might even be negative. But so the brightest celestial body in the sky is the sun. It has an apparent magnitude of negative 27. Remember, smaller the number, the brighter the object. The full moon is the second brightest celestial body. It has an apparent magnitude of negative 13. Notice the huge difference between those. That is a difference of 15, which is a difference of 1,000,000 in brightness. So the sun puts out 1,000,000 times more light than the full moon. Venus is the brightest planet. It has a magnitude of -4. And the brightest star, which is 8.7 light years away, and also a big bright star on its own, has an apparent magnitude of -1. That's right. Sirius has an apparent magnitude of -1. But it is the brightest star in the sky from Earth, excluding the sun. Now, the star's distance from Earth tremendously affects its apparent brightness. If you have 2 stars of the same brightness, but one is a lot further away, it's going to be a lot dimmer. So there's also something called absolute magnitude. Absolute magnitude is the brightness a star would have if it were placed 10 parsecs or 32.6 light years away from Earth. So for example, our sun has an absolute magnitude of +5. And Sirius has an absolute magnitude of, I think it's around, I'd have to look it up. It's about 0. It's much brighter than the sun. So if we know a distance to a star and its apparent magnitude, the absolute magnitude can be calculated. And it turns out the other way around works. If we know the absolute magnitude of a star through some other property of it and its apparent magnitude, we can figure out its distance. And that trick is one of the primary ways we figure out distances to things. We use the fact that if we have something that we know how bright it is, and then we can see how bright it is when we observe it on Earth, and that we can use to calculate how far away it is. So we have some time. I'm going to keep going. So the Hertzsprung-Russell diagram is a way to compare stars to each other. Like many things in astronomy, it has some sort of weird kind of backward scaling going on. But it results from plotting the stars' absolute magnitudes versus the temperatures of their photospheres. So you have the brightness on the y-axis and temperature on the x-axis, except for reasons having to do with how this diagram was originally made and what they were originally plotting. The hottest stars are at the left side and the coolest stars are at the right side. So it's sort of backwards. Most stars become brighter as they get hotter. The hotter a star is, the brighter it is. And these stars plot as a narrow diagonal band in the diagram that's known as the main sequence. So about 90% of the stars in the sky fall on this diagonal band called the main sequence. And the remaining 10% or so of stars fall in some of the other categories. So the hottest and generally brightest stars are blue. So one of the ways you can tell the color of a star is, temperature of a star is its color. Like, if something is glowing red hot, if you make it hotter, it will glow white hot. If you made it even hotter, it will glow whitish blue. So the hottest and generally brightest stars are blue-white. The coolest and generally least bright stars are red. And it turns out, because of the way that light, the emission of light with temperature works, it is possible to work out what the color of infinite temperature is. It's a sort of nice pale blue. But this allows you to study stars, and it turns out studying the Hertzsprung-Russell diagram allows you to get ideas about get a surprising amount of information about stars, including about how they form and die and things like that.
When looking up at the night sky, you can be forgiven for thinking that all the stars look similar, but each one has its own unique properties. From Earth, there are two easily observable and measurable stellar features, brightness and colour. But plotting these two properties of stars on their own doesn't really show anything, as observable brightness is affected by another crucial factor, stellar distance. In other words, even though one star may appear dimmer than another, it could actually be brighter, but just further away. When astronomers realised that they should take stellar distance into account, they were able to work out the actual or true brightness of stars. The Hertzsprung-Russell, or HR diagram, is named after the two discovering astronomers who used observational data to create a graph to classify and study the evolution of all stars. They labelled one axis of the graph with absolute magnitude, or true brightness of the star, and the other axis with colour, which is linked to the temperature of a star and defines its spectral type. Stars begin their lives in large, dark, cool clouds of gas and dust called nebulae. Pockets within these nebulae can begin to contract, getting smaller, denser, hotter and brighter. These cores are known as protostars. A protostar with too little mass would be too cool and dim, and it will never become a star. And an excessively massive, hot and bright protostar would be too unstable. But if they have just the right mass and temperature, they begin to fuse the hydrogen gas into helium, and a star is born. Each star that is formed will take its appropriate place on the main sequence of the HR diagram. While they fuse hydrogen in their cores, stars spend their life on the main sequence. Like the majority of stars, our Sun is a main sequence star.
This is about the middle.
But when it runs out of its fuel, hydrogen, it will evolve off the main sequence, and as the Sun's hydrogen-fused core collapses, it will reignite and fuse the helium in its core into carbon and oxygen. Its surface will expand and get cooler, and the Sun will turn into a red giant star. As the helium in the core is exhausted, the Sun will evolve into a planetary nebula, blowing off its outer layers, leaving behind a small, hot, white dwarf star that is rich in carbon and oxygen. Stars that are more massive than our Sun fuse their fuel more quickly and evolve off the main sequence to become red supergiant stars. These supergiants are able to fuse even heavier elements in their cores. When they run out of all their fuel, they end their lives in a supernova, leaving behind a very hot but small neutron star or a black hole. So thanks to the work of Hertzsprung and Russell, astronomers can now work out where a star is in its evolution if they know its true brightness and temperature.
Betelgeuse is a. Don't remember if Betelgeuse is a red supergiant. If it's gonna go, not gonna go supergiant anytime soon. But there's some debate about how stable Betelgeuse is. But yes, Betelgeuse is a red giant.
Yeah,
I'm not sure if it's actually a red supergiant. I'm not sure if it's actually on the line for becoming a.
that's what the.
Oh yeah, it is.
Yeah, that's what they classify it as.
It's supergiant. It's big enough. That was more of me not remembering, not.
Yeah, right.
But it's on this chart, so you can see that it's a red supergiant. It will eventually go supernova. Yes.
It's supposed to explode in the next 100,000 years.
Well, there was a whole debate about whether it was more unstable than we thought because it dimmed recently.
Oh, yeah.
But that may have just been like a cloud or something. I mean, around Betelgeuse, but
Right.
so some stars don't fall on the main sequence. The main sequence is where stars spend about 90% of their lifespan, so 90% of stars end up on the main sequence. The giants and supergiants are stars that are dying. Smaller stars become giants. Bigger stars become supergiants. When a smaller star dies, it leaves behind a white dwarf, like here, which is just the hot core of a star that is slowly cooling. And when a big star dies, it explodes. And you can leave behind either a neutron star or a black hole, depending on the mass of its core. I believe the Betelgeuse is in the scale that would leave behind a neutron star. So several types of stars do not fall on the main sequence. Red giants are very large stars that are cool yet still very bright. So they actually are generating more energy because the total luminosity corresponds to how much. But they got so hot in the center that the outer layers expand, so the outer surface cools down. So that energy is just spread out more. The very brightest are called red supergiants. White dwarfs are stars that are very hot and very dim, yet very dim due to their small size. Because white dwarfs are not actually generating any energy. They're just radiating off the heat they have. But they're super, super hot, very, very dense, and it takes forever for them to radiate off that heat because they're so small. So white dwarf matter is electron degenerate matter, and it's so a white dwarf about the mass of the sun would be about the size of the Earth. They're super dense. And well, let me just check. And there are variations. So spectral analysis of stars shows that even the most distant stars contain the same elements we find in our solar system. Basically, all the stuff we find out in our solar system, we can find in distant stars, we can find in the sun. However, there are variations in the spectra that depend on the temperature of the individual star's photosphere. Basically, depending on the temperature, the lines for various elements get stronger because they get more or less excited. And what elements are ionized changes in the surface. So it turns out the patterns of the absorption lines of the spectrum can be used to determine both the composition of a star and its surface temperature. Mass. Oh, it's pretty massive. It might go to black hole. I don't remember the line for return center black hole. Therefore, the patterns in the absorption lines of the spectra, yeah. And so this is convenient rather than trying to use color because there are things that can affect what we see as color. Like if dust gets in the way, it can absorb some color, some frequencies more than others and change the color. So that method is not always the best way to get temperature. While spectral classes are great because they're not affected as much by intervening material. So the spectral classes, there's 7 spectral classes. They go O, B, A, F, G, K, M. That's because initially they were measuring the strength of a certain individual absorption line. And so A class stars have the strongest hydrogen absorption line. I think it's the hydrogen absorption line. But that process peaks at a certain temperature. So above that temperature, it actually goes down, and below that temperature, it goes down. Below that temperature, it goes down because they're not as excited as much. You know, above that, I think, yeah, it's an absorption line, but, you know, then they're not absorbing as much. Above that temperature, it goes down because the hydrogen gets ionized, and the ionized hydrogen takes over, and that has different spectra. But yeah, so that's why the letters seem kind of random. It's because the original set of letters, which were A, B, C, and so on, were describing the strength of one of these lines. But the strength of that line peaks at a certain temperature. And so the actual pattern of letters that corresponds to temperatures is weird. And then more letters have been added as time goes on and stuff. But it's O, B, A, F, G, K, M. There's a few other ones that are for special cases, generally much cooler stars. But yeah, those are the spectral classes. The hottest is O, the coolest is M. Our sun is a G class star. And that's the horizontal top axis here. And our sun falls close to the middle of the main sequence and is a class G star. Sirius is quite a bit hotter than the sun, it's a class A star. And astronomers have found the majority of stars are small, cool, class M stars, also called red dwarfs. So Proxima Centauri, the closest star to Earth beside our sun, is a red dwarf and is a class M star. I think I will stop there for today. So have a nice day. There's a quiz today in SI, and I'll see you all next week.